Okay, so in this video, we are going to cover the concept of KEQ and equilibrium. Equilibrium governs reversible reactions. So before we can really get into how to calculate these things and really the understanding of it, we need to talk about reversible reactions. So in order for a reaction to occur at all, the reacting particles and the collisions between those reacting particles have to generate enough energy to overcome the activation energy for a particular reaction to turn reactants into products. And so we see this if we look at a general reaction of A plus B to produce C plus D. In order for A and B to become C and D, they have to produce enough energy in the collisions to overcome the activation energy hump. If the activation energy isn't achieved, then the reaction will not occur. And so in what we call a reversible reaction, the collisions of the product particles, so in this case, C and D, are able to also generate enough activation energy to overcome the activation energy in the reverse direction, which is different than the activation energy in the forward reaction. So what I have noted here on our little potential energy diagram is the activation energy of the forward reaction. Notice that it's an endothermic reaction. My reactants are lower, my products are higher. And so my activation energy is the amount of energy that it takes for me to get from the energy level currently contained in the reactants up to the top of this hump of the activation energy where the reaction actually occurs. In the reverse reaction for this one, our activation energy is actually reasonably small. My activation energy hump is reduced. But even if this was a larger hump in the reverse direction, it doesn't really matter. Whatever the products are, those collisions have to generate that activation energy if the reaction is going to be reversible. So if the activation energy is generated, then my C and D can go back and form A and B. And when those two processes occur at the same time, okay, we have a reversible reaction. And as the reversible reaction takes place, if the rate of the forward reaction, meaning the time it takes for A and B to produce C and D, equals the rate of the reverse reaction, C and D turning back into A and B, we can reach a state of equilibrium. So equilibrium is then defined as the state where the rate of the forward reaction equals the rate of the reverse reaction. And once equilibrium is established, the concentration of the reactants and products won't change because you constantly have the same amount of reactants being made into products and products being made into reactants, and it just becomes cyclical. Now, it is important to note that the concentrations do not change once equilibrium is established, but the concentrations don't have to be the same, right? I could have, 10 molar here and 4 molar there. As long as the same amount of A and B is being made into C and D is being made into A and B, the 10 and the 4 won't change. The rate has been established to be equal. So the concentrations are unchanging, but again, not necessarily equal. And once equilibrium is established, that rate is going to maintain itself unless it is acted on by an outside force, like the temperature is changed, or reactants are added, or products removed. And this gets more into what we're going to talk about in our next video, which is Le Chatelier's principle, how a reaction at equilibrium responds to a stress. But we'll save that for the next video. And as it turns out, one of the biggest things that will affect equilibrium is temperature. Equilibrium is highly temperature dependent. Okay? So the relationship between the forward and reverse reactions at equilibrium can be mathematically determined by calculating the equilibrium expression, or the equilibrium constant. And that gives us a numerical depiction of what is going on in terms of who is favored at equilibrium. Do I have more products? Do I have more reactants? Or are they equal? Okay. So the equilibrium expression allows us to determine which species, either products or reactants, are favored at equilibrium by looking at a ratio of those reacting particles. So the general form of K, which is what we're calculating here, is products over reactants. There are several different Ks. In particular, we're going to be looking at Keq today, which is the equilibrium K, but you also have KSP, which is the solubility K, which is a whole different thing. So just know that for whatever K you happen to be looking at, regardless of what subscript is here, it's products over reactants. That's the arrangement. And in this particular case, these square brackets stand in for concentration. Remember that concentration is in molarity or molar. And so anytime you see square brackets, you need to also realize that that means molarity. Okay. Alrighty. So this gets into all of those things I just said. So several applications of our general form, we're focusing on KEQ. KEQ only includes gases and aqueous ions. Liquids and solids are left out because they have a fixed volume, and because they have a fixed volume, their concentration doesn't change. In particular, when we talk about solids, we do talk about it in terms of KSP. KSP talks about the dissolution of a solid. For example, if I had solid NaCl breaking down into Na plus Cl minus, that would be something we would look at KSP for to see how much of the NaCl breaks up numerically. Okay. Whole different video. All right, so how do we write a KEQ expression? So here's our general form, right? If I have my equation where I have A moles of A and B moles of B producing C moles of C and D moles of D, my KEQ expression, putting my products over my reactants, is the concentration of substance C raised to the power of C, the concentration of substance D raised to the power of D. Whatever those mole numbers are, those are my powers. Concentration of A raised to A, concentration of B raised to B. And this is just my general form. I can add and remove letters from this as needed. If I have 4 things on the top and 1 thing on the bottom, that can happen. If I have 4 things on the top and nothing at the bottom, that can also happen. So just whatever I need, products on top, reactants at the bottom. All right, so what does K tell us? Well, if my KEQ is greater than 1, remember that means that I've got the products on the top and the reactants at the bottom. That means that my value of the products had to be bigger, right? Because I'm dividing here. So if my KEQ comes out to be greater than 1, I have more products than reactants at equilibrium. Products are favored. If we tie that in with what we learned about Gibbs free energy, that means I'm going from reactants to products. I'm going to have more products. That means that reaction is occurring. It's probably going to be favorable, which is going to give us a negative delta G. If my KEQ is less than 1, right, that means that my top number is small, my bottom number is big. I have more reactants at equilibrium. So in that same vein, right, that means I'm sitting over here more so. My reaction's probably not being very thermodynamically favorable. I'm probably sitting over here at unfavorable. Delta G is positive. If K equals exactly 1, then reactants and products are perfectly equal at equilibrium. Well, what does that mean about delta G? Well, if it's not negative and not positive, what is it? Delta G is equal to 0 at equilibrium. Okay. For my folks going on to take AP, that relationship is really important. All right. So let's do some examples of writing KEQ expressions. These are one of the easiest things that we'll have done all year. So really, there's only 2 rules. No liquids or solids, and you have to write KEQ equals. If you don't write KEQ equals, you just have this random fraction floating in thin air for no reason that doesn't mean anything. So KEQ equals must be part of what you are writing. All right, so let's look at our first one. H2O gas yields H2 gas plus O2 gas. So the first thing I'm going to do when I see this is go through, and if there's any liquids or any solids, I'm going to cross them out. I don't have any of those here, so I'm going to go into writing my KEQ expression. So KEQ equals products on top. So I've got the concentration in square brackets of H2, and I have a coefficient of 2, so that becomes an exponent to the second power. And then I've got O2, and I only have 1 O2, so I don't need to write to the first power. It's obviously to the first power. I only have 1. over, now let's go to our reactant side. I have 2 H2O, so the concentration of H2O squared. And that's my Keq expression. Writing Keq expressions are your like jumping off point to everything else that we do here. So it's really important that you make sure that you're getting this right. Because if you were to then have to plug in values to this, if your Keq expression is wrong, then whatever math you calculate based on that is also going to be wrong. Okay. All right, let's look at our next one. So 2NaCl liquid yields an irreversible reaction, 2Na liquid and Cl2 gas. Well, no solids, no liquids. So get rid of this, get rid of that. What do I have? I only have the Cl2 gas. So Keq is my Cl2 a product or reactant? It's a product. So that means I'm going to have that as Cl2. Now I can do this as Cl2 over 1, but it's unnecessary. I know that is over 1 when I just read it this way. Now, if this was reversed just for conversation, then what would I need to have? If this is reversed and my Cl2 is now reactant, my Keq would be 1 over the concentration of Cl2. All right. Next one. CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O liquid. All right, no solids or liquids, so let's get rid of that. And everything else is a gas, so we're good to go. Keq equals products, concentration, CO2 over CH4 and O2 squared. All right, and one more just to beat a dead horse. All right, 2Bn solid plus 3F2 gas yields 2Bf3 solid plus N2 gas. All right, no solid, no solid. Right, what's left? Keq equals concentration of N2 over the concentration of F2 cubed. All right, easy enough. So again, make sure Keq equals, coefficients become exponents, and everything needs to go in their individual brackets. All right, so now let's talk about how we use this, solving Keq expressions. So my first step is just what we did. Write a Keq expression. And then look at your Keq expression, see what it's asking you to solve for. Sometimes you're going to be asked to solve for the value of Keq. Sometimes you might be given Keq and asked to find one of your concentrations. So you may need to rearrange. And then once you've rearranged, if it's necessary, plug in and solve. The hardest thing about this is making sure that what you have written on your paper translates to this guy. Notoriously, this is something where you have it right on your paper, but how you've typed it in is incorrect. So what I would really stress is important is as you're going through the video, pause me and try to put your stuff into the calculator to make sure you're getting the same answer that I'm getting. If you're not, it's how you're putting it in here that's wrong. And I'll talk about some tips of how I put things in kind of as we go through. All right, first example. So given SO2 gas plus NO2 gas yields SO3 gas and NO gas. And then I'm given a bunch of concentrations, concentration of SO3, concentration of NO, concentration of NO2, concentration of SO2. Find the value of Keq. Okay, so step 1, write my Keq expression. Keq equals any solids or liquids? Nope. All right, all good there. So Keq equals concentration of SO3 times concentration of NO divided by concentration of SO2, concentration of NO2. All right, done, good. Now let's plug in. So SO3, 0.60 times NO, 0.25 divided by SO2, 0.15, and NO2, 0.35. All right, so pretty easy. There's no exponents on this one, so it's pretty straightforward. Biggest thing you need to watch out for is you need to make sure that these multiply together before they divide. If you type this in without putting the bottom part in parentheses, you're going to multiply here, it's going to divide by that, and then multiply your answer here, and that's not going to work. So what does this give me? To 2 sig figs, this comes out to be 2.9. So how do I record my answer? Keq is unitless, so it doesn't have a unit, but you need to be explicit about what this value means. So my answer is going to be KEQ equals 2.9. And what does that mean? It's bigger than 1. Therefore, products are favored. Okay, I have figured out the number, and I've also given it some context. All right, pretty easy. All right, let's go on to our next one. All right, cover that one up for a second. Number 2, given 2A gas plus B gas yields C gas plus 3D gas. So just a generalized equation here. And you're given concentration of A, B, C, and D. Find KEQ. So similar to what we just saw. All right, first step, write my KEQ. Everything's a gas, so I don't have to cross out anything. KEQ equals concentration of C, concentration of D cubed over concentration of A squared and B. Okay, so now let's plug in. All right, so C, 0.25 times D, 1.5 cubed over A, 2.0 squared, and B, 0.50. So again, watch how you're putting in, especially the bottom. And that should come out to 0.42. So again, KEQ equals 0.42. Therefore what? Well, it's less than 1. So reactants favored. All right. Seems pretty easy, right? It's because it is. Let's go on to the next one. All right. Given 2BN solid. Ooh, I'm going to go and cross that out before I even go any further because I saw solid. Plus 3F2 gas yields 2BF3 solid. Get rid of that guy. And N2 gas. And then I'm given a bunch of concentrations. Find KEQ. Now, notice what I did here, right? I gave you numbers for all 4 parts. But hopefully we realized I don't need that and I don't need that. Well, if I don't need those, man, I also don't need the numbers that associate with those. You're given the numbers basically to make sure that you realize, oh wait, I don't need those. So be observant. Just because you have numbers doesn't mean you actually have to use them all. Sometimes they're just there to throw you off. All right, find KEQ. So what's left? KEQ equals the concentration of N2 divided by F2 cubed. All right, plug in. So 0.63 divided by 0.45 cubed. 6.9. All right, so KEQ equals 6.9, bigger than 1. Products favored. All right, so I think we're pretty good here. Now, those have all been to solve for KEQ. The next thing we're going to look at is how to solve for a particular concentration. Now, with these concentration ones, there's a lot of different chemical equations out there. You guys should know that by now. I can't possibly show you a perfect example of everything, but we're going to do 2, and we're going to talk about the algebraic moves that you're going to make here. You should all have the algebra skills to be able to do the manipulations I'm getting ready to show you. I would highly recommend when you do them, you manipulate your equation when it's in the form of KEQ before you plug numbers in. It will make your life a lot easier. From my experience over many years teaching students, I find that the students who do it when they manipulate it when it's still in the form of an equation have more success than the students who try to plug in the numbers and then manipulate it, for what it's worth. Okay, so I would try to do it with the equation first. All right, so let's look at this one. Given 2A gas plus B gas yields C gas plus 3D gas, a KEQ value of 4.5, and the concentrations of C, D, and B, find the concentration of A. So just like what we've done in the previous 3 examples, we're going to start by writing our KEQ expression. There's nothing here for me to cross out, so KEQ equals concentration of C, concentration of D cubed over concentration of A squared, concentration of B. Now, it wants me to find A, which means, right, I need to isolate A. I need to get A by itself. I need to get A off the bottom of a fraction because no one wants to solve for the inverse of anything, right? And I need to get out of this square. So I'm going to go through the steps of doing this. I realize that you guys have the math ability to combine some of these steps, but bear with me. I am going to do it one step at a time, this first one, so that everyone can see all the manipulations. So first thing I'm going to do is I'm going to multiply A off the bottom and get it to the other side. So concentration of A squared, KEQ, equals C D cubed over B. And then I'm going to divide by the KEQ. Concentration of A squared equals C D cubed over B and KEQ. So I've gotten A by itself in terms of it's not with any other variables, but I'm not ready to plug in and solve yet because this is still squared. So to get rid of the square, I'm going to take the square root of both sides. And that's going to give me A equal to the square root of C D cubed B and KEQ. And now I'm ready to plug in, okay? Just kind of side note, had this been cubed, it would be cubed root. Had it been 4, it would have been fourth root. You know, whatever root it is, knock yourself out. All right, so now I'm going to plug in. A equals the square root of, let's see, where's C? 0.25 times 1.5 cubed over B. 0.5 times KEQ, 4.5. Now, depending on the calculator you have, you might have one where you can type all this in underneath the square root and it'll do that. I would recommend, personally, to do the inside, get an answer, and then take the square root. It's up to you. But when you type this in, what you should get is 0.61. All right, so let's look at kind of one way to do that. Hopefully there's not a glare up here. So 0.25 times 1.5 cubed divided by 0.5 times 4.5, and then square root all that. Please let this be right. Oh, good. There we go. All right. So that's how I personally would do it. It is up to you. It is personal preference. But you don't want to do beautiful work on your paper and then it goes to in your calculator. Okay. Now let's talk about units here at the end. You have solved for a concentration. So there's a couple different ways that you can give this to me. You could say brackets, because that means concentration of A equal to 0.61. You could say A equals 0.61 molar. Heck, you can even go total overkill and say brackets equals 0.61 molar. I'm okay with any of those. Just don't say A equals 0.61 naked without an M. All right. And you don't have to tell me products or reactants favored here because this is not a KEQ value. This is a concentration. Okay. All right. Let's do one more of these real quick and then cut you loose. All right. For this last one, you've got your equation, KEQ, H2O, and O2, find H2. So KEQ equals, let's write our expression, products, concentration of H2 squared times concentration of O2 over concentration of H2O squared. And this time I'm being asked to find the H2. Well, in this time, the H2 is on the top, so I'm actually going to leave this where it is and move all the rest of the stuff away from it. All right, so I'm going to combine some steps this time since you watched me do it piecemeal the first time. I'm going to multiply the H2O across, and then I'm going to divide by the O2. So that's going to give me concentration of H2O squared KEQ divided by O2 equals concentration of H2 squared. And then how do I get rid of the square? I'm going to take the square root of both sides. So H2O squared KEQ over O2, take the square root of all that, equals H2. And then come up here and plug in. So concentration 0.35. Oops, that's not what I'm going to do. I'm going to make that a parenthesis. Squared times KEQ value, which was 2.3, over 0.44. We're taking the square root of all that, equals concentration of H2. And when I calculate, that gives me 0.80 molar for the concentration of H2. Okay, go forth, calculate KEQ.